Kabla ya kwanza mwezi wa 12 tutakuwa na tuition kubwa sana ambayo itatoa huduma kwa masomo ya physics, chemistry na mathematics ambayo itafanyika IGOMA Mwanza. Kwa hiyo kwa yule ambaye anahitaji kujiunga anaweza kuwasiliana nami kupitia namba za simu ambazo ataziona kwenye screen ambazo zinapita, kwa njia ya WhatsApp, kwa njia ya SMS, kwa njia ya kunipigia moja kwa moja, nitampa maelekezo. Kwa wewe ambaye umekuwa ukitamani kufanya huduma na mimi moja kwa moja katika masomo haya ya sayansi ambayo ni physics, chemistry and mathematics, kutakuwepo na mafundisho makubwa sana. Tafadhali usiache kujiunga. Kwa tutafanya kwa nguvu kubwa, kwa ubunifu mkubwa, kwa jitihada kubwa kuhakikisha kwamba kila ambacho tunakitoa kwa mwezi mzima kitakusaidia, kama sio kwa mwaka mzima basi angalau robo tatu ya mwaka mzima wa masomo ujao hautahangaika. Kwa wewe mzazi au wewe mwanafunzi, uwe ni mtu ambaye unarudia mtihani mwakani, njoo ujiunge na tuition hiyo ya mwezi wa 12 ambao nakuhakikishia mimi nitakuwepo na nitakuhakikishia kwamba kile utakachokipata ni bora zaidi ya vile ambavyo unategemea. Kwa kutakuwepo na theories ya physics, chemistry na mathematics, alafu kutakuwepo na practicals za physics and chemistry kwa standard kabisa ambao unahitaji na kwa ubunifu mkubwa. Asante. Now we learned much about the stoichiometry, and we did some examples on how we can use this principle of stoichiometry to solve different questions. But that was not enough for me to make sure that now my students are very well understood about this one, or they are very well aware about this one. So I have decided to come up with 3 questions. The first question is right here, and we will be having the second question and the third question. Through those questions, if now you be careful and will be following me what I'm doing here, I am sure that you will be having something. So I've written 3 questions, and I'm going to solve one question after another. And when you look at these questions, you will find every question have got different strategies on how you can solve. So we'll be having different strategies on how you can solve questions about stoichiometry. Now, this first question is that sodium sulfate reacts with barium sulfates. The reactions between sodium sulfates and sodium sulfate and barium sulfate, as you can see from the equation, this is sodium sulfate that is aqueous, and this is barium sulfate that is aqueous, to produce solids and aqueous. Now means that the reaction between sodium sulfates and barium nitrates will produce barium sulfates and the sodium nitrates. Then the question is, what is the mass of barium sulfate that will be produced when 3.56 moles of sodium sulfate reacts completely with barium nitrates? So the question is to determine the mass of barium sulfate, here it is, that will be produced when the sodium sulfates reacts completely with what we call it barium nitrates. So the reaction here and the question here is all about the sodium sulfates and barium sulfates. It's all about sodium sulfates and barium sulfates. Others, we don't care how much you use, but what we care, how much you have used in sodium sulfate to react with barium nitrate, where the excess barium nitrate to produce what barium sulfate, including sodium sulfate. But we care about barium sulfate
and sodium sulfate. The first important thing is to understand the need of the question and relationship between what is produced and what is required. From the question, what is the mass of barium sulfates? That will be produced when this amount of substance of what we call it barium, sodium sulfates, react complete with barium nitrates. So we are just talking about it, sodium sulfate and barium sulfates. So those are the things. Now from the equation, from the balanced equation, we are having here one more and we are having here one more. Means that one more from the equation, this is from the equation, one more of sodium sulfate produces one more of barium sulfate. That is from the equation. This is from the equation. From the equation, that is what we have seen, that one more of sodium sulfate was used to produce one more of barium sulfate. This is from the equation. What from the question? From the question, this is from the equation. From the equation, what we've been given is 3.564 of sodium sulfate. What if now we have 3.56 more of sodium sulfates? What if we have that one? That will produce what? That is from the question. From the question. Now, from the question, what we've been given is 3.56 moles of sodium sulfates. And the question is, what is the mass of the barium sulfate? So we have to know the mass, first of all, we have to know the number of mole that was produced when 3.56 mole of sodium sulfate that was used. But from the equation we have seen, 1 mole of sodium sulfate was used to produce 1 mole of barium sulfate. What if now we have 3.56 mole of sodium sulfate will produce what amount of the substance that will produce? Well, that will be produced of what we call it barium sulfate. From the equation, because the ratio is 1 to 1, once you cross multiplication, you will definitely find the number of mole of barium sulfate that will be produced is equal now to 3.56 mole. Why is it so? Because the ratio is 1 to 1. That is 3.56 times 1 divided by 1. That is something that exists that will be having this one. But this is not a question. The need of the question is to determine the mass of the barium sulfates. But what we have got here is the number of mole of barium sulfate. Therefore, from we know number of mole is equal now to mass over molar mass. That is mass over molar mass. Molar mass of what? Molar mass of barium sulfates. Now, we have to know first of all the molar mass of barium sulfates. Remember, the molar mass of barium sulfate, that is the barium sulfate. Now, barium is relative atomic mass of barium 137 plus that of sulfur 32 plus that of oxygen 16 times 4, that is 64. Now, from here now, we are having this one. Now, the molar mass of barium sulfate will be 233, that is gram per mole. This is molar mass of barium sulfate. Therefore, since we are having molar mass of barium sulfate, and then we are having number of mole of barium sulfates, if that is the case now, we are just looking for something called mass. From this formula, number of mole is equal to mass over molar mass. Once you close multiplication, the mass will be equal, the mass of barium sulfate will be equal now to amount of the substance, that is number of mole of the barium sulfate times molar mass. But remember, number of mole, we got 3.560, that is mole. Then times molar mass. The molar mass is 233, that is gram per mole. Mathematically, more and more will get out. Then we'll be having only gram. Once you multiply that one, you'll be having, it is 829.48. That is approximated. That is mass of barium sulfate is 829.5. This is a gram. So the most important thing here is to understand, what are you just talking about? Are you talking about the reactants and the products? The products and the reactants. What is it? It's between what and what? Here we were just talking about it, sodium sulfate and barium sulfate. And this is discovered from the question, what is the mass of barium sulfate that will be produced when 3.56 mole of sodium sulfate reacts completely with barium nitrates. So the question is between the sodium sulfate that was used to produce barium sulfates. Now, what we used to produce what about barium sulfate? And from the equation, we are having this number of mole. Once you have balanced the equation, you look at the numbers, the quotients that is behind the number, that is quotient of sodium sulfate and quotient of barium sulfates. When you look at the equation, you find there is one here and there is one here. This implies what? 1 mole of sodium sulfate that was used to produce 1 mole of barium sulfate. That is from the equation. But from the equation, what you've been asked is all about barium sulfates that was used to produce when 3.56 moles of sodium sulfate. And therefore, we have 3.56 moles of sodium sulfate to produce what? And since the ratio is 1:1, means the number of mole that was used to produce the barium sulfate is the same to the number of mole that were used to produce, and that was used in the sodium sulfate to produce barium sulfate. And that is why now we got 3.56 as mole of barium sulfate. But the need of the question is not about it. Number of mole is all about to determine the mass of barium sulfate. And therefore, from the question we learned about it, more concept is that the number of mole is equal to the mass of a molar mass. Therefore, the molar mass is the total relative atomic mass of the compound. And therefore, by using this principle is where now we determine what we call it and relative atomic mass, total relative atomic mass of barium sulfate as a compound. Therefore, we get 233 gram per mole. This is all about the relative atomic mass of the barium sulfates. Therefore, this is what we call it. We call it molar mass. Once we have got the molar mass, we get back to the formula and then we apply. The concept is that the number of mole is equal to mass over molar mass. So we are having the number of mole, we are having the molar mass. We are missing what we call it mass. And therefore, once you cross multiplication, you find mass is equal to number of mole times molar mass. If that is the case, now we multiply them by mathematically, this mole and mole cancel out. Therefore, we remain with what we call it gram. And that is the SI unit of the mass. Why do we prefer using gram? Because when we're talking about chemicals, we have to understand we're just talking about minimal things, and that is why we use gram. Once you multiply this number mathematically, you get it is 829.5 gram. And this is the mass of what you call it barium sulfate, and this is what we've been looking. So you got to be very careful in solving about this question because you have the strategies to follow and we have principles to follow. And they are very simple once you understand the concept from one point to another. Now let us check the next question. Here is the second question, which reads as, the equation below shows the reactions between heated copper 2 oxide and ammonia gas. So the reactions between the heated copper 2 oxide, here it is the chemical formula, and the ammonia gas, here it is a chemical formula. Therefore, once you react between copper 2 oxides and ammonia, the result will be produced. We are having copper, nitrogen as a gas, and also we are having water. So these are the products that will be produced once copper 2 oxide reacts with the ammonia gas to produce copper as solids, nitrogen gas, and water as a liquid, not vapor or a gas. Because we have two things to discuss. Sometimes we may have water as a gas, that is water vapor, and also water as a liquid. And I explained about the things in my concept. The question is, if now 20 grams of copper oxide that was used to react with ammonia, 20 grams of copper oxide that was used to react with ammonia at STP, same temperature and pressure, calculates the number of mole of copper oxide that was used. If now you are having this number of mole, you are having this gram. How many moles that are used to react with ammonia? Now we are having this 20 grams of copper oxide. So we need to convert this one to number of mole. Definitely we know it. And the second question is the volume of ammonia gas that was used also. Once you have now copper oxide, then that was 20 grams that was used. Therefore, what is the volume of ammonia gas that was used in the reactions? And the third question is the mass of copper formed. Now, if now we use this 20 grams of copper oxide to react with the certain volume of ammonia gas, what is the mass of copper that was produced? It is all about comparing. For the first question, is all about not comparing because we've been given what we call it 20 grams of copper oxide. Now, we are having 20 grams of copper oxide. This is what we have. There is a mistake that students make. There is mistakes that students make. One of the mistakes that students make is that they confuse. When they are just doing something, they prefer to use these three without comparing. That is a mistake. If now you are looking for the molar mass of copper oxide, don't use this one because this is not a part of copper oxide. It is a part of copper oxide once you are reacting with this one. But now we are just talking about copper oxide alone. There is nothing that is incorporated with copper oxide. So don't use this number so as you may find out the molar mass of this one. No, it is something that does not exist. Now we are having this one. So we use number of mole is equal to mass over molar mass. Mass is something that we've been given, that is 20 grams. And then we are looking for the molar mass of copper oxide. Molar mass of copper oxide is that copper is 64 plus. Now this is oxygen, is now we are having 60, which now is equal to 80 grams per mole. This is molar mass for the copper oxide. Therefore, we divide it by 80 grams per mole. Mathematically, this cancels with this one. If that is the case now, this becomes more. It is therefore, it is 20 over 80. Mathematically, 1 here it is 4. Therefore, you are having 1 over 4. This is more. Once you convert to decimals, you have number of mole of copper oxide is equal now to 0.25. This is number of mole. Therefore, we have answered the question number 1. That is A. Determine the number of mole of copper oxide that was used since you've been given 20 grams of copper oxide. So we definitely convert this one into what we call it number of mole. And we know that how to convert this one, we use this principle. Number of mole is equal to mass of the substance over molar mass. And this is the relationship between molar mass, and number of the substance. So once we have got this one, we are through about question number 1. That is A. Then the second question is all about it to determine the volume of ammonia gas that was used. If now we are looking for the volume of ammonia gas that was used, now we are just comparing two things. We are just comparing two things, which is copper oxides and the ammonia. Once you look at the equation, you find we have something here. Here it is. That is it. 3 moles of copper oxide was reacted with 2 moles of ammonia gas. Now, that is 3 moles of copper oxide was used to react with 2 moles of ammonia. That is how it is written from the equation. It is not according to me from the balanced chemical equation. That is why it is very important for us to balance the equation first of all. Once you find it is unbalanced, you balance it. But if you find it is balanced, you don't need to balance it. But check out and use what it is written there. And that is why we have 3 moles reacted with 2 moles of ammonia gas. Therefore, the question is the volume of ammonia gas that was used. But this is from the equation. But from the equation, we are having 0.25 mole of copper 2 oxide. If now we have 3 produces 2, what if now we have 0.25 mole of copper 2 oxide? We reproduce what? Therefore, you cross multiplication. You find it this time this one divided by this one. It is 0.25 times 2 divided by 3 because we cross multiplication. This time this one you get 3(1) and this time this one you get that one. Therefore, you are looking for the value of phi. It is where now you this one and this one you divide by this one. Number of mole of what we call it number of mole of ammonia that was used is equal now to 0.17 mole. This is number of mole. But from the question is not all about to determine the number of mole. It's all about to determine the volume of ammonia gas that was used. If that is the case, we know the relationship between the volume and number of mole is very simple. We have number of mole is equal to volume over molar volumes. Molar volumes. Now remember, molar volume is something constant. And it was written, it is 22.4, that is this meter cubic per mole. That is molar volume. It is something constant. And therefore, once you close multiplication, you find volumes. Volume is equal now to number of mole times molar volumes. Now, number of mole, with that it is 0.17 times, that is mole times what we call it molar volume, 22.4, that is decimeter cubic over mole. Mathematically, more and more cancel out. Therefore, what we are having here, we have to multiply. It is 3.80 decimeter cubic. And now, the volume that will be used of ammonia is 3.8. Now, you have got the volume that was used is 3.80, that is decimeter cubic. We have got this one by comparing, because it's all about comparing copper oxide and ammonia. From the equation, we have 3 moles of copper oxides that was used to react with 2 moles of ammonia to produce 3 moles of copper as a solid, 1 mole of nitrogen as a gas, and 3 moles of water as a liquid. Therefore, that was the question. Therefore, we were required first of all to compare ammonia and copper 2 oxide. That is what I've done. It is here. Once you have this one, we have number of mole of copper 2 oxide. Now, that number of mole of copper 2 oxide will produce watts of, we require watt of ammonia. This is what I've done. Then in cross multiplication, you find the number of mole of ammonia that was used is 0.17 mole. Once you have got the number of mole that was used, therefore you refer back by knowing that the number of mole is equal to the volume over molar volumes. Therefore, molar volume is exactly which is there, as I said, it is something constant, and number of mole is something that we got. Therefore, we are looking for the volume. You cross multiplication, you find volume is equal now to number of mole times molar volume. Number of mole we got 0.17 mole times the molar volume, that is 22.4 decimeter cubic per mole, or liter per mole, because once you're talking about liter and decimeter cubic, those are the something that have got equal quantities in the relationship. That is to say, 1 liter is equal to 1 decimeter cubic. Now, let us see for the next question. The next question is the mass of copper formed. The mass of copper formed. We are no longer comparing copper oxide and ammonia. Now, because we are no longer talking about ammonia, we have done about it. Now let us talk about the copper 2 oxide and the copper. Now, when you look at the equation, you find here there is 3 more and here there is 3 more. That is to say, 3 moles of copper 2 oxide was used to produce 3 moles of what we call it copper as a solid. Now, what if now we have this one, 0.25 mole of copper oxide will produce what? That is what we got from the first question, because from the first question we were talking about to determine the number of moles of copper 2 oxide that was used. It is here now we have done. It is 0.25 for the first question we did it. So if now from the equation we have 3 moles of copper 2 oxide that was used to produce 3 moles of copper, that is what I've written. What if now I'm having 0.25 moles of copper oxide? What will be used to produce? That will be produced. Since the ratio is 3 to 3, that is 1 to 1 because it can be simplified. Therefore, also the number of mole of copper that will be produced is 0.25 mole. That's how it is. But the question is not to determine the number of mole. So we have to use this number of mole to convert to the mass. By definitely, you know, the number of mole is equal now to mass over molar mass. But we are looking for the mass. We cross multiplication. Therefore, mass is equal now to number of mole times molar mass. Remember, the molar mass is represented by capital letter M. And therefore, the number of mole we are having is 0.25 times molar mass. Number of mole, that is mole, times molar mass. Molar mass of copper is 64, that is gram over mole. This is what I'm learning. This cross multiplication. Therefore, the mass of copper that will be produced is equal now to 0.25 times 64. Now it is 16 grams. So this is the mass of copper that will be produced. So it is all about comparing. The ratio is 1 to 1. Why is it so? Because 3 and 3 can be simplified. Once you cross this and this one, you find it is 1 to 1. If now it is 1 to 1, it is simple. Once you cross multiplication, you get 0.25 times 3 divided by 3. 3 and 3 cancel out. You remain with 0.25. Now, this is what I've written here. Therefore, this is number of mole of copper. But the question is not to determine the mass, is to determine the mass of the copper formed. Therefore, you convert this number of mole to the mass. And that is how it is done. Mass is equal now to 0.25 mole times 64 grams per mole. Once you multiply them, you get it to 16 grams. This is what we've been looking for. And we got to be very careful to talk about this one. Now, this is the second question. Now, let us see the third question, and which is the last question to discuss about stoichiometry in the third questions. The last question here is that lead nitrate decomposes on heating as shown in the question below. Here it is. The question is all about the composition of lead nitrate to produce this one. This is a decomposition reaction. It means that this was heated so as it may produce lead oxides, nitrogen dioxide, and oxygen as a gas. Then, that is from the balanced equation. 112 decimeter cubic of oxygen. 112. That is 112 decimeter cubic of oxygen. That is here. Was collected when a sample of lead nitrate was completely decomposed by heat. A. Calculate the mass of lead nitrate sample. A is to determine the mass of lead nitrate sample. If this lead nitrate was used to produce this oxygen, once you look up the question, you find here 2 moles of lead nitrate was used to produce 1 mole of oxygen. That is the question. That is to say, 2 moles of lead nitrate was used to produce 1 mole of oxygen. That is from the question. and it must be the balanced chemical equation. What if now you've been given 112 decimeter cubic of oxygen? We require how many moles? That will be required, so as we may produce 112 decimeter cubic of oxygen. From here, we are having volume, and the comparison is between number of mole and number of mole. So we are having no point on how we can use this volume. Otherwise, we convert this volume. If now we convert this volume, means that we have to use number of mole is equal to volume over molar volume. But we are having volume here, which now is 112 decimeter cubic. Then we divide by molar volume, that is constant, 22.4 decimeter cubic per mole. Mathematically, this will be taken to that one. And therefore, once you take this one, you count this one, you find 5 moles of oxygen. So instead of using this one as a volume, we prefer to use number of mole. Why is it for? Because the relationship here was all about number of mole and number of mole. Once you've been given a gram or volume, you have to use the formula so as you may convert this one into number of mole. And therefore, we are no longer using this one. Instead of using this volume, we use number of mole, which is now 5 moles of oxygen. Will be used to produce what? Therefore, Euclid's multiplication. It is therefore now we are having 2 times 5 divided by 1. Now the number of mole of lead nitrate that will be used to produce 5 moles of oxygen is equal now to 10 moles. So this is the number of moles. These are a number of moles that was used to produce 5 moles of oxygen. So 112 decimeter cubic was collected when 10 moles of lead nitrate that was used. And that is the question is the mass of lead nitrate. If now you are looking for the mass of lead nitrate, it is something very simple for us to understand it. So we know number of mole is equal now to mass over molar mass. Therefore, molar mass of lead nitrate is obtained once you have taken the total relative atomic mass of the compounds. Atomic mass for the Pb, that lead, it is 207 plus. Now the atomic mass of nitrogen is 14 plus. Now the atomic mass of oxygen 16 times 3, that is 48. Therefore you multiply them by 2. At the end of the day, they will be 331, that is gram per mole. That is the molar mass. Once you have got the molar mass, the question is to determine the mass. Euclid's multiplication. Now closing multiplication, mass will be equal now to number of mole times molar mass. But remember, number of mole we have got it is 10. That is 10 mole times the molar mass. We got it at 331. That is gram per mole. This is what I got. This cancels out. Therefore, the mass of the substance is 31. That is 0. This is gram. So this is the mass of what we call it lead nitrate that was used to produce what we call it 112 decimeter cubic of oxygen. So this 112 decimeter cubic of oxygen was collected at STP when the sample of lead nitrate was completely decomposed, and that lead nitrate that was completely decomposed is that 3,310 grams. That is amount. That is 10 more. Instead of using this one, this is equal to this one. This gram is equal to 10 moles. So this is what we call it, the mass that was used. Now calculate the mass of the lead nitrate that was used. The second question, calculate the mass of lead 2 oxide produced. The mass of lead 2 oxide. Lead 2 oxide is here. This is lead 2 oxide. Now there is 2 here and there is 2 here. That is to say, we have got, this is 2 moles of lead oxide, lead nitrate, was used to produce 2 moles of lead oxide. But remember, we got from the first question, we got 10 more of lead nitrate was used to produce what? Since the ratio is 1 to 1, the ratio is the same. That is 1 to 1. Also, the number of mole that will be produced of lead oxide will be the same. It is therefore, we are having the number of mole is 10 mole of lead oxide. But the question is not to determine the number of mole, is to determine the mass of this one. Therefore, the molar mass of lead oxide, that is the total relative atomic mass of lead oxide, is equal now 207 plus. It is now 60. It is therefore, we are having molar mass, it is equal now to 223 grams per mole. This it is. Therefore, the question is to determine the mass of the substance. From, we know, number of mole is equal to mass over molar mass. Therefore, mass is equal now to number of mole times molar mass. Remember, number of mole, we got it is 10 times. This is 10 mole. Times now, molar mass, it is 223, that is gram over mole. This is where we got it, this one. Therefore, if that is the case, we are having 2, 2, 3. That is 0, that is gram. Now the mass is equal now to 2230 grams. So this is the mass of lead 2 oxide. Now the mass of lead 2 oxide that was produced, here it is. It is very simple. We have compared. After we have compared, now we close multiplication. Once we have closed multiplication, we got in this one. Once we have got this one, this is the mass. So means that we are definitely looking for that. Now the last question is the volume of nitrogen gas that was produced. The volume of nitrogen gas that was produced. Talking about it, the volume of nitrogen dioxide that was produced. Here it is. And also here it is. Now, we are having from the equation, we have 2 and 4. That is 2 moles of lead nitrate was used to produce 4 moles of nitrogen dioxide as a gas. What if now having 10 moles of lead nitrate? Remember, this 10 moles comes from where? We got it from the first equation. When we are using this one of oxygen, we got that 10 moles of lead nitrate was used to produce 112 decimeter cubic. So we are still using it. Now, we close multiplication. This is 10 times 4 divided by, it is 10 times 4 divided by 2. Now this is 2, now it is 20 moles. Now, we are having 20 moles of nitrogen gas that was produced. But the question is not about number of moles. The question is all about the volume. But remember, number of moles is equal to volume over molar volumes. Now, volumes. V is equal now to number of moles is equal now to 20 mole times now molar volumes. Molar volumes is equal now to 22.4 decimeter cubic of what we call it mole. This cancels out. Therefore, the volume now will be equal to 448
that is decimeter cubic. This is what I know. Now, the volume will be equal now. The volume that is V will be equal to 448, that is decimeter cubic. That is the volume. So, you have to know, by concluding about stoichiometry, it's all about comparing the reactants and the products. What you have used to produce what? That's what we are talking about. And that is why, throughout the equations, we have compared this and this one, so as we may obtain the something that is very important. Now, 105 decimeter cubic of oxygen gas that was used to produce what? So, it is all about comparing. It is all about to see what you have used to produce what. The amount that you have used to produce it, what kind of amount. So that is the end of the discussion of what we call it stoichiometry study questions. And I think there is something you have learned. Now, please don't forget to subscribe our channel. Thank you for watching.